Hello, welcome back everyone to day 2 of this Edwards Symposium on Soft Matter. Delighted to see you all again and delighted to welcome back our virtual attendees. So without further ado, I'd like to pass you on to Camille Scalio, who is going to be our chair for the next session. Thank you.
Okay, so thank you, Jane. So this afternoon we will have 2 sessions. So the first one will be about functional gels and energy materials, which I will be chairing. So the first speaker that we have is Emanuela Delgado. She is a professor at Georgetown University, and she's expert in using computational statistical physics to address problems around soft materials, but also in order to design new environmental friendly materials. So we're very much looking forward to Emanuela's talk, which will be about particulate gels. So thank you very much for joining, and we're passing it to you.
Hi, so thank you for having me, and really sorry that in the end I am still stuck on the other side of the screen. I hope we'll be able to get back completely in person soon. So this is the session on functional gels and energy materials, and I think that in both cases one of the main strategies is to try to embed some high-value functional components into nanoparticles, macromolecules, small aggregates in solution, which then can further aggregate on larger length scale and form gels that look like this. Let me see if I can switch my my slides. And so these are, you get this porous spanning networks that provide rigidity, transmit stresses, allow for some reconfiguration under load, and so on. So in the end, these are really the materials that then we can eat, squeeze, spread, or 3D print. But the point is, of course, there is enormous challenges on how you do this in terms of embedding the high value functional components, mainly from material science and chemistry. But the question that I want to address here is rather, okay, once you're able to do that, do we know how to use? In the sense, do we know how to predict how these structures will behave? Sure, we know a lot about gels from polymer physics, but in those gels, actually the chemical architecture provides some good guidance on how to develop theories and how to predict the way the material will behave. Whereas this gel structure, they look much more messy, and they seem each one different from the other. And so the question is it possible that even in these cases, with this messy gel structure, there is actually some sort of hidden beautiful architecture? Where does it come from? And is it actually determining the way the material behaves? So the point is that in each of these systems, the phenomena that initiate gelation can be very different from system to system. And within the context of colloidal gels, there has been a lot that has been understood and a lot of insight that has been gained into how actually you can form gels starting from equilibrium processes like phase separation, spinodal decomposition, microphase separation, or non-equilibrium processes like diffusion-limited processes, fractal growth, and so on. All these studies has taught us a lot. For example, if I know something about the microscopic forces, let's say, for example, from the LBO theory for colloidal systems, then I have an idea of the phase diagram, and then I know, thanks to these studies, now I know where it's more likely to actually get gels, and what is the initial morphology, the local morphology that I would see, because I know what are the processes that sort of initiate the aggregation of the system. But one thought is that in the end, in all these systems, no matter from where I start actually this first aggregation processes, in the end what I have is always some large-scale growth of different type of structures, which eventually becomes frustrated. And this is what produces basically the gel formation, no matter from where I start. So basically this idea that I get some growth that is frustrated then leads to the point that there must be always some kind of stress, some amount of stress that is built in this structure that corresponds to the gel formation. And because of the disorder, this actually manifests in some localized stress pattern, which then may be actually the feature that controls the mechanics of this system. So to think a little bit more how these localized stress patterns can emerge and how can they be organized actually during the gelation process. So let me say just a couple of things about elasticity and rigidities in this system. So this, I don't know if you can see my mouse. So this is a cartoon we proposed some years ago with Alessio Zaccone, where basically we were saying, okay, you have a colloidal solution with different volume fraction, different strength of interactions. Let's say you know something about the forces, so you can identify which part of the phase diagram the system will be likely to undergo a phase separation between a particle poor and a particle rich phase. And then somewhere under this region, because you need the aggregation processes to be strong enough to basically initiate the gel formation, then somewhere under this region, I'm going to see some transition from a liquid-like to a solid-like behavior. But which type of local structures, in which way they will assemble on larger scale and then determine this frustration, how does this happen will depend not only on the volume fraction of the solution, so the amount of solid material that I put in, and on the strength of the interaction, but also on the kinetics, on how I go through this line, basically, or I cross this region, depending on the condition in which the gelation is occurring in my experiment. And so in these cases, however, we could show that in fact, if you, for example, consider some specific type of structures that can occur in this type of phenomena, like for example, if the particles first start together, lumps together into clusters due to the attractive interactions, and then the clusters are elastically connected also between them, again, because of particle-particle interaction. So we could show that in these cases, basically, it's just a subset of all the elastic connection that you've built in the material. So the cluster-cluster connection that in fact determine mostly completely the elasticity of the system. So already there is a seed that there is a subset of actually the structure that I built that end up playing a major role in the mechanics. The other point that I want to make is that in this system, actually, because I need interaction strength that is sufficiently high in order to start build these aggregates that are sufficiently stable to then grow into these larger scale structures and then form the gel, then thermal fluctuations are there, but they play, in most of the cases, I would say, a minor role in the development of elasticity, in the development of the elasticity of the system. The elasticity is mainly enthalpy in nature, and one of the implications of this is that then just connectivity, pure connectivity is not enough actually to provide rigidity. So I can have a fully connected net like here, but if I don't have enough thermal fluctuations that introduce an entropic cost for changing conformation in the system, basically this fully connected net, it's not necessarily going to be also rigid. And so if my elasticity is mainly determined by enthalpic type of effect, then what happens is that I need to have a specific organization of the structure that is there in order to produce rigidity. And just being connected to a certain number of neighbors, it's not actually enough. Or just to have one connected object through the system is not enough to produce rigidity. So we've studied these issues in this system with Xiaoming Mao and Zeb Bracklin a couple of years ago, where basically we were pursuing this idea that in fact in the emergence of rigidity in the system should be looked at as a rigidity percolation problem. So where you start first to build this local rigid structure, which then connect into a spanning percolating network. But this is not quite the same rigidity percolation that has already been studied a lot for, in general, for disordered materials, where basically you consider that these structures are going to be connected sort of randomly because of the disorder of the system. The idea is that because of all these microscopic processes that can be equilibrium, non-equilibrium, that that initiate the gelation, and then the frustration that emerges as some kind of collective process, then the connection between this rigid structure and the formation of the rigid structure itself must come from very strongly spatially and temporally correlated processes that are basically coming from density fluctuations in the system, microscopic dynamics that is spatio-temporally correlated, and so on. And so we tested this idea, first developing a lattice model for correlated rigidity perturbation, and then we tested it through molecular dynamics simulations. And so we could see that, in fact, these correlated processes, what they do is that they can favor the formation of sort of smart thin structures, in the sense of smart because they are particularly specifically optimized to transmit stresses, and the fact that they're thin is important because then they can grow and span the system and favor the presence of a percolating network, even with a small, very small amount of solid materials, so solid particles at hand. So with a very small amount actually of elastic connections that are there. So like, for example, one example is this kind of war and truss type of structure that emerged naturally in our lattice model, and is well known in architectural engineering to be a structural element that can actually carry substantial stress, a substantial load in bridges and buildings and so on. And so then the idea that one of the consequences of that, as I was alluding to, is that actually now because there is this self-organization that is coupled to the emergence of rigidity, then this would be one thing that explains how I can get a solid with actually a tiny amount of solid material at hand, because this tiny amount of solid material is actually highly specifically organized. And this is in fact what we see in these colloidal gels, and also wider in particulate gels, that I can get a solid response with a relatively tiny amount of solid material. And so, of course, this is hard to see in experiment, because if I look at the structure, how would I recognize this essential rigid structure that is growing in the system? There is a lot of other processes that are going on that are not necessarily directly bringing in the important connections, and they do not necessarily contribute to the localized stress pattern that I would like to see. But indeed, in the last few years, there has been a couple of experimental studies and experimental combined with simulation, that combining imaging and biology have been to see elements that are consistent with the scenarios that we've described here. So the consequences of the fact that there is this kind of rigid structure emerging through the system, you can also see them because then this changes the microscopic dynamics that spontaneously can occur in these gels. Again, now I'm showing you simulations, and I'm not telling you how the simulations are done, but I will do that in a minute, so bear with me. So basically, we've done simulation of a model, three-dimensional model of one of these gels, where we were breaking the structure, part of the structure, to watch how these processes would induce stress fluctuations in the system. And we were watching at the relaxation processes that would be the consequences of these events, as it would happen during aging of the material, that it's due to the presence of small thermal fluctuations or to the relaxation of internal stresses that are built in during the solidification. And so what you can see is that basically this, because the thermal fluctuation can be very, very small, actually most of these fluctuations are driven really by the elasticity. And because they're driven by the elasticity, they are strongly correlated in space and time, which leads to very intermittent dynamics. And the result of this is that the microscopic dynamics that we see results into compressed exponential, faster than exponential type of relaxation processes. And this is what we've seen in simulation, but in fact, it's been seen over, I would say, nearly more than 20 years in a number of experiments, indeed, in a number of similar and wider range of gel materials and soft materials. the fact that there are actually subparts of the structure that play a crucial role, and there are this localized stress pattern, become even more evident if you now start to subject the material to deformation. This is again one of our simulations. This is in 3D, and I'm showing you the network that is being shared. And you see part of the network, I hope you can see the movie okay. You see part of the network that becomes sort of thicker, and this is our visualization of where tensions tend to accumulate as we are shearing the material. So you can see that from the beginning, actually, there is a very small portion of the material where this tension tend to accumulate. And what is interesting is that actually this region where tensions accumulate are sort of determined from the topology of the system. So there is a softness, a local softness, or a local stiffness in the material that it's determined by the way the network is spatially organized, and the connectivity of the network is spatially organized through how the topology is actually spatially organized. And the presence of this region, in fact, control the possible emergence of microscopic precursors to failure, the localization of failure in the system, and basically pretty much a lot of the even nonlinear response of the materials. And again, this is something that has connection with a number of phenomena that have been observed directly or indirectly through rheology in a number of experiments. So I think I've given you some, what I've tried to do so far is to introduce this idea that actually these structures are very messy, but there is, in fact, ideally a subset of this structure that is responsible for the mechanical behavior of these materials. And we can see the fact that this should be there by following how rigidity should emerge in this material, by thinking that ultimately the gel formation is always the result of this frustration in the growth of these aggregated structures. And then we can see this localized stress pattern very clearly when we subject the system to a load. And so now I've shown you all these, some of these results from simulations. And what I would like to do is actually tell you a bit more of how we do these simulations. So the idea is that we wanted to have a model where we can study these large-scale organizations of this network, and we can study the stress redistribution as the materials are being subjected to deformation, or as we study the spontaneous dynamics, type of dynamics that emerge in these systems at rest. So in order to do this and to be able to perform large-scale simulation that would allow us to statistically access this information, then we need to have some, we need to think, well, what are really the microscopic degrees of freedom that we want? So we need to make some approximation of what happens, what are the microscopic ingredients that we put in. And the essential microscopic ingredients that we have identified are, let's start from particles. So we have a discrete system, and these particles interact, the interactions between the particles are sticky, so we need, as I was saying before, strong attractive interactions to make the aggregate stable enough against thermal fluctuations. And then, but then we also consider that, in fact, once these particles are connected through this or are close by, very close by through these strong attractive interactions, then they have to be actually their contact. They can be in sometimes solid and solid contact. There are irregularities on the surfaces, maybe in some, in all sorts of situations that I can imagine from this type of cartoons that I see here. But also particles can be really the first colloidal particles, or the nicely spherical colloidal particles, but they could be just lumps of particles that I was mentioning before, or particles of different irregular shapes and so on. So to start to be able to, of course, to do this, to have this more complex contacts than just what you would obtain from the two-body attraction between the center of the particles, then you need to introduce more degrees of freedom. And so the simplest thing that we could do to have some of these effects in our model is basically to add to our usual two-body short-range attraction that people use in colloidal system, a three-body term that contains an angular modulation to this three-body attraction. So basically, if I have two particles that are stuck to each other because of the attraction, the third particle that comes in will see a potential energy that in fact it depends also not only on the distance between particle 3 and particle 1 and particle 3 and particle 2, but also on the angles that these bonds form. So here I have this energy profile the map of this, the contour plot of this energy map that this third particle would see if it approaches these two particles that are already attached together. And so you can see that for certain choices of our parameters that enter this mathematical expression, there are these regions where the particles can be attached. And gain energy, whereas there are regions which are basically forbidden, where the particle will not be able to remain stuck there. And so, sure enough, we can change this. We can change basically the parameters in this model and encapsulate and include many different cases and many different scenarios. But for this talk, I want to focus on this specific choice of parameters that I'm showing you here, because this leads to the formation of a gel network with a number of different gelation protocols that we have tried, that basically has a structure that is relatively simple, where we can identify two structural elements. So either particles are basically forming one particle thick strands. So these basically these gel strands that you can see here, and then these gel strands branch and connect to form these larger scale networks. So these branching points are, of course, very important for the frustration, for the development of the frustration that I was discussing before, but not only. And so now it's interesting. So changing the gelation protocol, changing the volume fraction of the particles that we have, we will have different degrees of frustration that emerge in our system and in the growth of this different type of structural element in different part of our simulation box. What we can do is that from the analytical form of our interaction, now we can compute what is the energy cost, the elastic cost, energy cost in deforming these structural elements alone. So if we take a chain made of 3 particles, how much it costs, how much energy it costs to bend it or to stretch it, and this is this contour plot that you see here. Or if you take a branching point, how much it costs to deform it by changing the angles. So once that we have the expressions for this elastic energy cost, now we can compute the modulus that we would predict for the gel if we consider just adding up all these structural elements as if they would contribute independently to the elasticity. And then we can do other simulations, and we can basically perform rheological tests on our gel as it is there and obtain the modulus from that. So in this plot, the empty symbols are basically the modulus that result from adding up this different structural element in the statistics in which they are relevant, they are present in our gel network, but where each elastic contribution is computed independently from each other. And we can combine them, of course, in different ways, in series, in parallels. For example, imagine that they are connected in series or in parallel in our network. Or we can measure the field squares. They are the whole modulus that we measure from. And so we can see that at low volume fraction, basically, just adding up these elements as if they were independent, we can basically justify the whole elastic modulus with the specific combination of these elements. But if we go to higher volume fraction, then there is clearly a significant part of the modulus that it's actually not captured by just this combination of these elements as if they were independent. So this tells us that indeed the topology plays a very important role in what is the part of the structure that determines the mechanics of the system, that it's not just by identifying what are the structural elements that are there that we can actually come up with the prediction of what's the modulus of our gel, especially when these materials become more and more coupled, which is what happened with the emerging frustration during the gel as it increases with increasing, for example, the volume fraction of the system, or as it could happen in experiments by changing the way I prepare my gel, the kinetics of gelation. And so then basically this tells us that again, the topology plays an important role in determining what is the structure that is ultimately important for the mechanics of it. And in fact, we see this recurrent theme of the topology in, for example, in this study that we have done on the binary hydrogels with Bert Meyer and Dimitris Vlassopoulos, these very interesting binary hydrogels that they've been making and of which they've been studying the rheology, where basically you have one component that forms a network of semi-flexible fibers, and the other component that forms micelles that would not form a network on their own, but they can get embedded and somehow contribute to the mechanics when you combine the two of them. And so what we've seen by using simulations, basically building on the previous model, but of course adding these characteristics of these two components. And so what we basically realized is that it is the space topology that is set by the first component network that then determines how much the second component can actually modify the mechanics of the resulting composite. And so this actually explains the non-monotonic dependence of the viscoelasticity on the composition of the binary hydrogels they were working with. But it also actually makes a point of how controlling the formation, the development of the topology through the spatial organization of the network, it's a very important aspect of designing this type of functionary binary hydrogels. So to conclude, I just want to give you a kind of sneak peek of, or a teaser of a paper that is about to come that we're currently writing up. And this is a collaboration with the Garrett McKinley group. So where basically what we have done is now we have studied a wide number of these gel produced with this model, where we have even the same structural elements as I was saying before. So the interactions parameters are the same, but then we can vary the volume fraction of the gels, and we can vary the preparation of the gel, as I was alluding before. And by doing this, we can obtain a wide variety of structures, even with the same volume fraction, and a wide variety of structure by changing the volume fraction. So if you change the structure, like going from the left to the right, you change not only the modulus, but the whole viscoelastic spectrum. And so, well, I'm back to the figure that I was showing in the very beginning. I have a lot of different structure, a lot of different viscoelastic spectra. So what? Well, actually, what we realize is that you can reconnect all of these gels into a unique viscoelastic behavior by building this type of master curve where all our gel end up being able to go. And this common viscoelastic behavior that can be actually recapitulated by a unique viscoelastic constitutive model has some interesting characteristic. One of this is that there is this extended kind of extended power law regime, which we think is very important. And in fact, it corresponds to the need of having this fractal element in the constitutive behavior. And this type of power law behavior, it's typically associated to the presence of a fractal structural characteristic in the network. But these network structures that we have, they actually never fractal. They don't show any fractal nature if we just look at the amount of particles that are there and how they're spatially organized. And it's actually by doing a very systematic analysis on all the structure that we realize that in fact there is a fractal characteristic in this network, but is hidden and is buried in the rest of the structure. And in fact, it emerges as the material starts to become rigid, because in fact it comes, this kind of power law regime is set at the very beginning of the, at the transition from non-rigid to rigid, and it is set by the first rigid backbone that emerges during gelation. So there is this kind of memory of the gelation process that is imprinted in this type of viscoelastic behavior that can recapitulate the behavior of all these networks. And when we putting these gels on this master curve basically point to time scales and an energy scales in these networks that actually all scale in a way that now we can rationalize in terms of these fractal characteristics. So the idea that there is an essential backbone that is responsible from the mechanics, it's interesting because it was already put forward in polymer system, for example, by Adolf Martin, and from all the people. I have just here a work from Paul Goldbart, but there is a wider community of people that in the context of polymer gels was studying the elastically active chain element in governing the mechanics of these materials. And so I've said in the beginning, there are differences with the physics of polymer gels, but now it seems that I found some theme that actually goes back to them. Okay, so now at this point, let me wrap up and conclude. And for this last story, I will point you to the paper that hopefully will soon be ready. And so basically what I've tried to convince you or to argue is that the way to understand these particulate gels that are so important for functional materials and in all sorts of materials in our practical life, from ceramics to cement to different type of hydrogels, basically, the key is to understand how these localized stress patterns emerge during the gelation process. Sure, the initial steps of the gelation process are important, but what is important is to understand how then the growth of this different structure generates frustration and builds in stresses which manifest themselves with this localized stress pattern in this disordered structure. And I've shown you how understanding the emergence of rigidity is a key point because it gives us important insight into what could be the organizing principle of this localized stress pattern. And in fact, I think that the idea of this localized stress pattern immediately connects the physics of this very soft materials where aggregation and interactions, microscopic interactions are being so studied in a number of contexts. In fact, it creates a connection between these materials and a concept like force chains in granular materials or even localized in excitations in amorphous solids. And I've showed you some teaser about the paper that is soon to come about how we find some indication of that in the viscoelastic spectra of a wide range of gels that can be all understood under with this concept that there is a fractal characteristics that governs the stress transmission, and this fractal characteristics develops as the rigidity emerge in the system and immediately creates a hierarchy of time scale and length scale, which maybe we can hope to understand across different materials and different systems. Thank you for your attention, and I'm happy to take any questions.
So thank you very much, Emanuela, for these very interesting talks. So we will be having questions both online, so please, virtual attendees, don't hesitate to write questions. And I can see that we already have 2 questions in the audience. So maybe... Let's go to Megan. So maybe the easiest is to say your name so that, can you see the audience or not, Emanuela?
Yeah, I can see some. I can see the person that is asking the question.
Hi, it's Megan Povey from University of Leeds. A very nice, very interesting talk. I was particularly interested in the use of the word energy cost. In a purely elastic network, that energy is actually stored. It's not dissipated.
Yes.
In the examples you're giving, it seems to me there are dissipation mechanisms as well, which will thermalize. I just wonder if you could comment on that, please.
Okay. So there are indeed, you're right, there is actually dissipation processes, and I guess that especially the last part, the last work on the viscoelastic spectrum tells us really how it's crucial to understand the coupling or the connection between the type of energy storage that you built in and the end of energy dissipation. And there is, of course, in the simulations that we do and in the experiments, right, these systems are always embedded in a solvent, and there are thermal fluctuations through the solvent. And so there is, in any case, energy dissipation at the level of the motion of the particles in the solvent. The motion is always damped. However, one can really see that because of the topology of the gel network, there are larger scale dissipation processes that are associated to, for example, the presence of softer, much softer regions, floppy regions that can, for example, follow the deformation, or that can be deformed at much lower energy costs. So really to understand the interplay of the two is central to all this business. So it's beyond just the rigidity. I agree with you.
Thank you. We have another question from the audience.
Hello, Emmanuel. It's Tom McLeish from York here. Hi. And hello to Peter, too, if he's anywhere around you. Lovely talk. Thank you very much. Some of the beautiful simulations and diagrams of the stress distribution, the highly inhomogeneous stress distribution, reminded me of a piece of work we did actually in Leeds when I think Peter was there, but Daniel Reed, who's here, were involved, where we were looking at spinodal phases of polyurethane, so with very hard phases and very soft phases, so it's like your systems. And what came out of there is the topology as well. So I wanted, you showed us the distribution of stress, but I wondered if you'd seen anything that I remember we saw in the distribution of strain, which is a completely, well, it's a complementary field, of course, particularly around topological transitions like the critical percolation transition, where we saw huge broad distributions of local strain given as a response function to a fixed macroscopic strain, which is sort of a non-thermal, analogy of the fluctuations at a critical point. Now, I wonder if you've seen anything like that in these, and whether those also depend on the topology or topological transitions of your gels.
So we have looked into things that definitely point in the direction that you say. So, for example, in these simulations where we were locally breaking the gel and look at the stress fluctuations, where we saw this faster than exponential processes, for example, there definitely we have looked at the strain fields and seen how the strain fields actually is long-ranged, and it can be really described by continuum elasticity, which is surprising in a system that is so heterogeneous. On the other hand, in the simulation of the shear that you were mentioning, in fact, there we can see that we have studied the strain, the pattern of the strain field, and how it couples with the rate, basically to produce some very localized features. So that can lead to some kind of fracture, if you want, in this type of gels. So it's not exactly, but this is now, it's very anisotropic because we were doing this at large deformations. So it's not exactly what the same type of understanding that you developed in your study there with Daniel, but it's somehow consistent. All these pieces, they point to the same kind of overall picture, I think. And just another point note that I want to add is that I do think that maybe once that you start to consider this phenomena and supramolecular association in polymer system, then same type of processes that I'm describing here could be relevant also there. So that's why I think this is encompass a wider range of materials.
So, sorry, we have another question from the audience. So apparently, Emanuela, the people on the chat are saying that apparently you can hear the questions, but they can't. So could you just repeat the question before answering so that they have the question?
Yes, of course.
Thank
yes,
you.
yes. Sorry about that.
There's a question from Rafi.
Hi, Emanuela, talk. This is Rafi Blumenfeld from Cambridge. I am wondering about the significance.
Cannot hear you very much now.
Yeah. Apparently you have to do like a rock star, like really.
Right, okay.
Yeah. I like the pose.
Okay, Manuela. Rafi Blumenfeld. I'm wondering about the significance of the three-body force that you include. And what we see is something which is very similar to force chains in granular systems. And in granular systems, the forces are only compressive and extremely short range between particles. So if I take everything that we see in granular system, reverse the compression into attraction, and then try to do tensile, I should see exactly similar force chains, but there'll be tensile force chains. Now, in this case, we never needed any three-body interaction. So my question is, first, well, two questions. First, how would the structure of these stress chains that you see could tell you anything about the interaction on the particle level? And the other one, can I reverse engineer, essentially, if I know now the topological structure? Because we know in granular systems, the local topology really determines the structure of the force chains and so on.
Right.
So the question is, can we actually look at the structure that evolves and from that reverse engineer to find the local interactions? Sorry, it's a very long question.
No. And so Rafi is asking about what is, there are many questions. So one question is, what is the role of this three-body term that we put in interaction? How do we compare what we're seeing here with what has been seen in granular system, where basically the forces, the force chains are purely compressive, and then you can reverse the sign of the interactions and then generate the same force chains that are actually completely tensile. But in granular system, actually, the local topology completely tells you about the force chains. So how is this different here? Did I summarize it well?
Fantastically well.
Yes.
Okay, so the first point is about the three-body interaction. And so the three-body interaction, this is a slightly different question to me. So I think that this effect of introducing some local angular rigidity is there in a number of colloidal systems. And what is different is where it emerges. So in some cases, you could have really some angular constraint at the level of the single particle connections that is due, as I was, in this cartoon that I had on my slide, due to surface interactions between particles that basically block rolling and this sort of phenomena. But you could also have that the units that you are that this kind of local rigidity develops at larger scale, because you first form lumps, and then lumps have irregular shape, and this irregular shape actually determines lumps interactions that are not just spherically symmetric. So I think this is an element that is there in a lot of this colloidal or particulate system because of this microscopic physics. However, I don't think that the details of the specific of these interactions are actually determining necessarily completely the larger scale organization of what you could call them force chains, or of these localized stress patterns that we see. It's the larger scale organization of the system. That's why I made this point about the rigidity, because the rigidity, in fact, it's a really non-local property, right? There is a larger scale organization of the system that has to happen in order to get overall rigidity. And this becomes dramatically evident in this system because volume fraction here can be so low. So I think in the case of granular system, in most cases, and of course, please correct me if I'm wrong, the granular solid are very dense. So basically, the topology has to be more or less homogeneous, at least more homogeneous than what it is in these systems. Whereas in the gels, since the volume fraction is so low, you really end up having a lot of, you can see that there is a large scale heterogeneity that you can obtain in different ways with the same interaction. and even with the same amount of particles, but just changing the preparation protocol. So, you know, there is this famous, beautiful work about the stress-bearing structure and the formation of a force chain in granular system by Mike and Bouchot and Whitmer and Clodin. And so there the idea is that this structure that bears the stresses is completely determined by the load. And in this system is, I guess it's determined by a combination of the interaction, the process the microscopic dynamics that can happen depending on the type of microstructure that you have started to build, and then also possibly the load from our external forces.
Thank you very much, Emanuela. So there was a last question that we couldn't ask, but you just answered it. It was a question from Mike. So I think that we can end now. Thank you again very much, Emanuela. Let's thank you, Emanuela, again. So our next speaker is Alphonse van Bladen. He is a professor from Utrecht University. So he and his group use simple colloidal model systems, not only to address fundamental problems in condensed matter, but also by means of self-assembly in order to build new materials with extraordinary physical properties. So he will talk about, today he will talk about how to use dispersion droplets in order to do new materials which have apparently new photonic properties. So Alphonse, you have 40 minutes and around 5 to 8 minutes for questions. So we will be waiting for him to appear, and thank you very much again for joining.
Thank you also for the organizers for letting me talk to you today about supraparticles. And supraparticles is a word that we didn't choose ourselves. They are like supramolecules, particles build up from other particles, and like supramolecules, the forces between the particles are weak. Also in this case, the supraparticles, the forces between them are relatively weak. I'm certainly not going to be as bold as stating that supraparticles are an important new direction in soft matter science or science, but they're definitely an important part of our soft condensed matter research at Utrecht University in the Dubai Institute. So I'm going to address here, and I hope to not disappoint too many people, not that many gels inside these supraparticles. I will mention and show you one example of those, but that's an industrial example. But the approach that we take is very generalizable also to gel-like particles. It's important to mention as well that all the supraparticles I'll be talking about, and even the one that's right back to me on the screen, is itself still a colloidal particle. So built up from nanoparticles, and the particles, the supraparticles that I'm showing you here, if I highlight it with the laser pointer, these particles here are a few hundred nanometers in size themselves, so we can do a further self-assembly step. So what I hope to convince you of that these supraparticles and their self-assembly is a very powerful way of structuring matter at many length scales. I do not want to, in the end of time, skip over the most important people who did the work, and those with an asterisk here, you can download the thesis at our website, www.colloid.nl. And this is experimental work, mostly of Ernest van der Wee, Bart de Nijs, and Da Wang, but others contributed as well. But it's also a very strong collaboration between the computer simulation group of Marjolein Dijkstra, who talked yesterday. But it's also a collaboration within the Dubai Institute with the group of Daniel van Makelenberg, And it's a collaboration with University of Antwerp, the group of Sarah Bals, and University of Pennsylvania, Chris Murray. So, what is very important in the self-assembly of such nanoparticles in slowly drying emulsion droplets is that we are able to analyze them in real space. And our group has a very strong background on light nanoscopy, and I'll tell you with a few examples of what the recent advances are. But we've also ventured into electron microscopy tomography to elucidate also on the nanoparticle level, quantitatively in 3D, the structure of these kind of self-assemblies. So what is new in light microscopy, and we are now pushing that all the way to nanoscopy, so even having three-dimensional resolutions below 100 nanometers, is that we can not only determine in 3D the positions of spherical particles, but also of rod-like particles, and then also obtain the positions of the rods, but also their orientation in 3D. We can scan very fast, so extensive three-dimensional data sets can be scanned within on the order of a second. And this movie that I'm playing here is actually a projected 3D data set. So we can get the free diffusion of these rod-like silica particles, the synthesis which we developed about 10 years ago and can also be made fluorescent. These rod-like silica particles is described in this paper cited below. But the real space analysis is something that we developed in the last 5-6 years. So that movie was particles with motions in 3D. We can now go through a 3D data set, and this is a 3D sample that has been equilibrated in the gravitational field. So we see these rods going from the top to the bottom being many particle layers stressing on that by the osmotic pressure. So we first see a colloidal liquid of these rods, and all the purple is the 3D analysis of all these rods in the 3D data set, so we can find all their orientations. And then at some point you get a first order phase transition, and you get a liquid crystal, a smectic liquid crystal formed by these rod-like particles. So that's on the light length scale, and we're pushing that all the way down to 100 nanometers. But we also want to analyze structures on the nanoparticle length scale, so just particles of 10 nanometers or less. With light microscopy and confocal microscopy, we make use of the very high numerical aperture of the lens here in electron microscopy tomography, and this is actually an extension of the technique that you may know when you have a tomography done in the hospital, but then on a much smaller length scale. The numerical aperture is very large, so it means that a lot of the data is in focus. Several micron can be in focus, so we can turn the sample around, get different projections for different directions, and obtain 3D data sets that way. Marjolein, you mentioned yesterday this beautiful binary crystal, which forms when the size ratio of the big and the small particles is about 1 to 3. With scattering, you cannot really analyze what the structure of the small particles is. But by doing tomography, and this was work done about 10, 11 years ago in the Dubai Institute, we found that there are not only simple cubic lattices of the big particles, which have 3 times the size, but that the small particles have been arranged on an icosahedral lattice with an icosahedral symmetry around the big particles on the cubic lattice. So we can now also identify single nanoparticles with sizes of 10 nanometers in 3-dimensional data sets. This was just a crystal with 5 or 6 layers, but I'll show you results of crystals which have layer thicknesses on the order of 30 particles. So this is another example of a superparticle formed with gold nanorods, and notice here that the scale bar is 50 nanometers. So these particles did not have an aspect ratio large enough to form liquid crystals, but they're nevertheless important for plasmonic properties. So you only see by the contrast the gold nanorods. I should mention there is a mesoporous silica layer which gives them a thicker extension, and in the tracking this silica layer is not shown, but you can see that in 3 dimensions we get all the orientations and the particles, and even we can get their different because this was a relatively polydispersed sample, even the different sizes, all from the analysis of the 3D data sets. So just a few slides, because I think with this audience, I hardly need to motivate this, but why structuring on multiple length scales is so important. So Richard Feynman, and it's often said that he kicked off the nanosize revolution. It's not really true. The nanosize revolution happened on its own, and then a lot of people discovered this beautiful talk of Richard Feynman that he gave for the American Physical Society in 1959. And he literally was daydreaming. What could we do in material science if we could build up matter molecule by molecule or particle by particle? So the title of his talk is that there's plenty of room at the bottom. Well, his daydreaming now is everyday reality. You've seen the beautiful structures with the atoms of IBM formed already some decades ago, but now CO molecules can be put standing straight up on metal surfaces, giving, for instance, these beautiful fractal structures. And this is work of Ingmar Swart et al. So on the atomic and molecular scale, we can do what the daydreaming of Richard Feynman was about. What I think is very exciting is that we now start to be able to do this on the atomic molecular scale, but that we can continue doing this on multiple length scales. And to paraphrase Richard Feynman, there is even more room at multiple length scales. So why would you want to do that? For instance, just one example I'll show you. I'll show you lasing superparticles. So we're going to build up from core shell quantum dots. So they have a cadmium selenide core in which an electron hole pair can be generated, and it's strong function of the size of the semiconductor core. But then we make a core shell structure in such a way that when the particles are very closely connecting, that their wave function, their quantum mechanical wave function, doesn't overlap. So the very high quantum efficiency of this core shell system, and here is EDX showing that it's indeed a core shell structure, is such that when the particles are self-assembled in this particle of several hundred nanometers in size, the superparticle, that is then therefore very strongly luminescent. It's still strongly luminescent because the quantum mechanical wave functions don't overlap. So why is this interesting? Well, for trivial reasons, you can build up these superparticles with red, green, or blue quantum dots, and then make any color that you want. And you've probably seen that, and we're not sponsored by them, but that some televisions have much more beautiful colors if you use these quantum dots. They are much more easily processable if we make these quantum dots in a superparticle. So that's what we did, and just as an example, we made this beautiful white superparticles by mixing the right red, green, and blue colors inside the superparticles. And here you see some of these other superparticles. However, if we make these superparticles not a few hundred nanometers, which is interesting for televisions, but a few micrometers, then optical density of states start to be modulated quite strongly, because we get me-whispering gallery modes of these nanoparticles, and that modifies their emission. So we see here actually some zinc oxide rods which can be excited also with UV light, and in this cathode ray luminescence we see beautiful red luminescence of the superparticles excited by the UV excitable zinc oxides. So what we get if we have superparticles of a few microns in size is that in the emission in the red, you start to see individual modes being excited. And what is very exciting about this is that if we make the superparticles even larger, then these modes start to couple back, just as if they are two mirrors in a lasing cavity, starts to couple back non-linearly, and we get lasing superparticles. So then the very broad red emission becomes very highly non-linear when we select one of these modes. So what we've now done is we've structured on the atomic scale these quantum dots so that they don't couple with their quantum mechanical wave functions, but they very strongly couple with their optical density of states, so strongly that we get nonlinear effects and get lasing superparticles. That's just one example of why we want to structure on multiple length scales. But now let's just go to some of the fundamentals what was a real surprise to us, namely that if we do the self-assembly of particles of which we know the interactions quite well, then for superparticles built up from on the order of 100,000 nanoparticles, we found different structures as compared to the structures in the bulk. And this is well known for very small clusters, but as far as I know, it was not realized that this effect of the spherical boundary consists even when you have on the order of 100,000 of particles. So let's start by something that I don't need to explain in this audience. If we have particles with hard interactions, they form, and the free energy of close-packed crystals are very close together, but they form face-centered cubic crystals when we reach a volume fraction of 50 volume%, and then with the first order phase transition, you get crystals with a volume fraction of 55%. The free energy of the other close-packed crystals, like hexagonally close-packed, is very close by, but if you give the system enough time, they will form FCC crystals. This is my one example of superparticles with not equilibrium structures, but actually gel-like structures. But I did want to also mention in this Edwards Symposium that there is already a $1 billion, I've been told, market for supraparticles that are made on an industrial scale. So these are gel-like silica superparticles built up here from very small silica nanoparticles that have been also made in drying emulsion droplets, but because there was salt added and the particles are polydispersed, we don't get beautiful crystals, but we get beautiful gels. It's all in the eye of the beholder, of course, what you want to get. So this is an important market because this is coated with C18 chains, and then it's an inverse HPLC column. For the chemists amongst you, you know where that stands for, but it's to purify insulin, for instance, and therefore an important industrial product already. But what we want to do is make the particles very monodispersed, don't give them that strong interactions and attractions. And what we also want to do is not make clusters of just a few particles, like for instance done in the beautiful work in the group of Dave Pine, where all the particles were on the outside of the emulsion droplets. And of course, we're very well aware that even Ramsden and Pickering already 100 years ago used emulsion droplets to connect with colloidal particles as well. So there's definitely not that much news under the sun. But what is relatively new is that we are focusing on the self-assembly of the particles that are not at the interface, but that are dominated by the self-assembly of the particles inside the droplets. So this work of Pine, you create beautiful clusters, which are hugely influenced by the strong drying forces on the surface. Here, we look at the self-assembly of the particles in the bulk. What if we make the attractions not very strong is an important scalable property of our self-assembly, is that what we do for the self-assembly of nanoparticles, if they behave like with hard interactions, is completely transferable than if we self-assemble 1 micron size spheres in bigger droplets as well, or 100 nanometer size particles also for optical properties. So if the interactions are not strongly dependent, then we can scale our procedure to all different kinds of length scales. What's also very exciting, but because of time, I'll only flash up this beautiful example of 1 micron droplets that we can now make with microfluidics with 5,000 nozzles parallel at the same time. So we can create on the order of 1 day of flowing 1 gram of monodispersed droplets with sizes that are monodispersed enough that they crystallize and that have on the order of a micron in diameter. So that's very exciting, but I'm now going to focus what happens in 1 single droplet. So what we found already 5 years ago, and that's why I go very quickly about it. So we did this with iron oxide nanoparticles, which can be made very monodispersed. The polydispersity in size can be as small as a few percent. They have this single crystalline property inside the particles, which is important for some applications. What we found is that for these superparticles, for very large superparticles, we found what we expected. If you dry them slowly enough, you get face-centered cubic crystals, which some of you might be even able to recognize from this ABC stacking. These are beautiful, single crystalline, very large supraparticles. it was a very big surprise to us that smaller superparticles, but still on the order of a few tens of thousands of particles, like this is an example, I think, of 30,000 particles, had very complicated structures inside. And now that we are used to it, we can recognize it very quickly. There was five-fold symmetric structures here inside these superparticles. So as a little intro, many of you probably know that if you have one central particle and you want to solve the problem, how many particles can I get around that particle? That's 12. But what is the local densest structure of that 12 of those 12 particles? Some of you might think, if you know that in bulk packing, 74% is the highest packing, so it should be a fragment of a close packed structure. Well, that's not the answer. You can get it locally somewhat more compact, and a way of locally measuring the volume fraction is, for instance, to shrink wrap it. That's a good way of defining a local volume. You can also, of course, call that the Voronoi volume and the convex hull of that packing. But that packing of an icosahedron is slightly better than that of a close-packed structure. But an icosahedron has five-fold symmetries, so we cannot continue that in 3D, and that is very important. The cut-off structure of an icosahedron everybody knows as a soccer ball, but that happens also when we start to do self-assembly in spherical confinements. We get icosahedral structures and truncated icosahedral structures. So it was well known that the closest packing of hard spheres is this icosahedron, and even for many different pair potentials like the Lennard-Jones potential, that closest sum of distances also translates itself that the free energy of Lennard-Jones clusters, and therefore also of metals, for instance, gold or silver, is better with this icosahedral symmetry than for the bulk FCC crystal. So that was known. What was not known is that this argument also for hard spheres continues until you have about 9 layers of particles. So when you have on the order of 100,000 particles, then the free energy of packing is still dictated by the fact that icosahedral symmetry can have a lower packing fraction. If you continue to do this, to make this an infinitely large structure, then you lose out, because the volume fraction of these icosahedral packings are only 68% and not 74%. So what we found is these beautiful five-fold symmetric structures. If you're not used to looking at it, here is in the core the five-fold symmetry. And now that we are used to looking at it, we actually immediately recognize, oh, this is a rhombic-cozy dodecahedral surface-terminated structure. So that is one of the surface cut icosahedral structures that you can get if you try to fit them in a sphere. When we saw this happen with different nanoparticles, we weren't sure whether the attractions played a role or not. So we did it with micron-sized particles. We had to do it very, very slowly, but then we saw the same structure. So then we started doing computer simulations on this, and we found still the same icosahedral structures. So this is a computer simulation, one of the earliest done by Frank Smallenberg. So like 6 years ago, we couldn't find all the nanoparticle positions, but now we have advanced and we can easily get all the coordinates of all the nanoparticles. But even with this 80% of the particles found, we clearly saw the icosahedral structuring of the particles inside, which was exactly what we also found in the computer simulations. And as I mentioned, we also found it for micron-sized spheres, but then the drying has to be very slow. So to summarize our results, on the order of tens of thousands of particles all the way to 100,000 particles, you get icosahedral or surface reconstructed icosahedral structures. For very small, like few hundred to 1,000 particles, you get pure icosahedral structures, and that is quite interesting. What we are working on right now in our group, but the group of Vinny Manoharan was a little bit earlier than us, that is, if you do this not with nanoparticles, but with particles of silica, in this case with the diameter of about 300 nanometers, you get beautiful interference colors because of the interference of light. And because of the symmetry of the icosahedral structure that formed inside the superparticle, these colors look the same from all directions. So it's very interesting as a new kind of pigment, because this is not by absorption, but purely by constructive and deconstructive interference. So what now happens if we make the spherical shape slightly different? And the iron oxide nanocrystals that I talked to you about before can actually, by symmetry, and I'm not going to go into the details of that, be turned from all the way from a single crystalline spherical particle all the way to a sharp cube particle. It's not 100% sharp and cubed, because there is also a ligand layer around it. So it turned out that even this ligand layer of 1.5 nanometers thickness was important to explain the cell behavior that we saw. To make a very long story short, we defined a shape parameter. 1 is pure sharp cube, 0.8 is therefore almost cube-like, and then we found to crystallize inside the superparticles simple cubic structures. These are interesting, but for applications not that interesting, because if you burn away the ligands and you have the particles therefore become one supercrystal, so when you do directed attachment, as it's known in the field, then you get just one clump of a single cube-like crystal. However, what we did find is that if you still make the shape not completely round, but towards being more round, we went from simple cubic back to this icosahedral structuring. However, with this shape parameter of these superparticles that I'm showing you now, there was still enough flatness that the particles next to them still had the same crystalline orientation of the cube arrangement. So they didn't form simple cubic crystals, but they did form the same crystal orientation as their neighbors. So if we now burn away the ligands and make one crystal of it, it's an icosahedral crystal with holes in it, with a single crystal of the iron oxide. And what is very nice and not trivial at all is that we were able to not only determine the positions of all these nanoparticles, because remember there were only 10 nanometers in size, but even the orientation of these almost rounded cubes. Michiel Hermes was very instrumental in finding this out. And so here on the left is the superparticle is turning around, and then in the middle you see a cut through it. You recognize the 5-dot symmetry again. And all these colors that you see here are the local RGB values of the neighbors, so the three-dimensional orientation of the rounded cubes in space. And what you can see is that the same particles around a central particle have the same color. So they're still strongly rotationally correlated, but only to their next neighbors. The correlation function drops off quite fast. But for getting directed attachment in 3D, this is an important property, because the icosahedral symmetry is completely different than the cubic symmetry of their more sharp cubes. And we found exactly the same in the simulations, as long as we also took in the shape parameter the ligand layer into account as well. So a beautiful example, I think, where we're now working towards 3D directed attachment of these nanoparticles and of these single crystals. And it's not just as beautiful, because I don't know if you know about these coccolithophores, but these are single calcium carbonate crystals beautifully structured in this armored for these single cellular organisms. So we're not that as beautiful yet, but we're slowly getting there. So what now happens if we want to look at a binary crystal? So what we chose is a size ratio of the hard particles of 0.8. And I'm not going to go into the details, but these are called Lavis phase crystals, and you find them in metallic crystals. But very similarly to the hard sphere case, when you have a kind of ABC stacking of these binary layers, that's a very interesting structure. That's the equivalent of a hard sphere's FCC, but here it's magnesium copper 2. Why it's optically very interesting is because the big spheres form, if you burn away like the smaller spheres, for instance, they form a diamond lattice. And a diamond lattice is for photonic crystals very, very interesting. So conversely, if you burn away the big spheres and the small spheres are there, then it's also very interesting because that's called a pyrochrore lattice, and that also has a band gap for very low contrast, relatively low contrast. However, for bulk crystals, you don't get the magnesium copper 2 interesting phase, but you get the magnesium zinc 2 phase, which unfortunately is optically not interesting. So what we now found is that you can manipulate the self-assembly of these binary lattice phases by going to spherical confinement. So details are not so important. These are semiconductor particles, two different sizes. The bulk, in one projection, you get this magnesium zinc 2 phase, what is expected. To be honest, you actually get a random stacking just like in hard spheres, but that is not how the nanoparticle people present their results. But if you have the stoichiometry exactly right, you get beautiful icosahedral structures with, again, the 5-fold symmetry, and that now have locally this magnesium copper 2 symmetry. So optically, very, very interesting. What is still an open question, and although I'm convinced that this is actually a quasi-crystal, and we can discuss about it perhaps in the questions, you can also look at this as a binary icosahedral structure and not a quasi-crystal. But because these defect structures are never appearing in the center, I'm actually convinced it's a quasi-crystal. But this is for us in the future to find out. Just like icosahedral quasi-crystals, because we have this 5-fold symmetry, we get in the Fourier space the beautiful 5- and 10-fold symmetries that are exactly the same as that Dan Shechtman and Levine and Steinhardt, theorists who published a few months after Shechtman, and we get the same golden mean repeat unit in this Fourier space, but I'm not going there for the details. What is very intriguing and very interesting as well for both fundamental studies and applications, if the stoichiometry is slightly off, so here there is a majority of smaller particles, then we get binary crystals, but not the icosahedral crystals. So we have an idea why that is, but we can discuss that perhaps also if there are questions about that. But if the stoichiometry is right, then all the superparticles with a size of about a few hundred nanometers, so 100,000 nanoparticles again, becomes icosahedral. We very painstakingly also simulated this, and this were simulations that took many weeks. So we even saw that there was a nucleation and growth phenomenon happening in the growth of this icosahedral, what I think is a quasi-crystal. So with that, I'm almost to conclusions. And they're joking in the group already that if it looks nice, Van Blada puts it in a droplet and see how it self-assembles. That is kind of true, but what I hope to have also shown that both for applications, but also for fundamental studies, self-assembly in icosahedral, in spherical confinement gives a lot of surprises, and that this is a very powerful platform to do multi-length scale structuring. So these are some of the papers that have recently come out from this work in our group. Yeah, as I mentioned, we're working towards not only having dried supraparticles, but also supraparticles where we grow a silica shell around the emulsion droplet with the nanoparticles inside, and then with external fields can still manipulate the dispersions inside the supraparticles. So we call those dispersion supraparticles, and then the supraparticles become even tunable with respect to all their properties. If you want to see a little peek about that, perhaps there is time in the questions for that. So with that, I want to thank you for your attention.
So thank you very much for this very interesting talk. So I see that there is already a question on the virtual chat by Ravi Kumar Pujala. So the question is, why is the slow drying important?
Yes, so if you want to get glasses or gels, then the slow drying is not so important. But if you want to get to equilibrium, so it's now much better established that, for instance, these silica particles of 300 nanometers that were shown in the optical, you really have to dry them for 8 hours or longer. Otherwise, you don't get the icosahedral structuring. So for equilibrium structures to form, the drying needs to be slower than the self-assembly and roughly the self-assembly scales with the third power of the diameter. So for 300 nanometer particles, this takes hours. For 10 nanometer particles, because that to the third power is quite a lot less, you can probably get away by doing it in a few minutes.
Okay, thank
you. So it's basically to get equilibrium.
Thank you very much. So there is a question from the audience here. So again, keep the mic close and probably say your name.
Hi. So this is Daniel Reed. I'm going to ask what I think might be the obvious question on the quasicrystals. So the structure you're getting inside these spheres, which is the five-fold symmetry, is it something which in principle could be repeated out to infinity?
No. So
is it a quasicrystal then? Because quasicrystals,
yeah,
I think,
no,
should
there
be infinite.
There is a very subtle thing here. The icosahedral structures that we got from single particles, you would never call that a quasicrystal, even although that is never repeating itself as well, and it has five-fold symmetry. So where the subtle difference is whether the structure that forms in the sphere is every time the same structure. It would then still not be a repeat structure, or what I think it is, in this case, I think it is a spherical cookie cutter structure taken out of a bulk quasicrystal. So in both cases, you will never have the same repeat structure. So to be honest, we only analyzed on the order of 8 structures, because in real space, it's a lot of work. And in the simulations, we only got 2 or 3. But all those, there was never an exact repeat structure. But the Fourier transform was beautifully symmetric, 5, 10-fold, etc., like it should be for a quasicrystal.
Okay, I think there's a follow-up question. Just before that, can I ask someone in the virtual audience to say if you can still not hear the questions from the audience? Maybe someone can type the answer and we can continue. They can hear, okay, thank you, sorry. So the follow-up question.
So yeah, it was just a comment. So I think what you're describing as the spherical cookie cutter was what I was getting at. So if it is a spherical cookie cutter, I think I said that right, then it is a quasicrystal, I think.
I completely agree with that, and I think that's what it is, but we don't have yet enough coordinates to know that for sure. But that's exactly the point. So it's a subtle point. But by the way, for applications, it doesn't matter, because they both have icosahedral symmetry, and for 100,000 particles, it will not give different structures. But for a fundamental, it's important to know whether it's the one or the other. So we hope to answer that in the future, near future.
Okay, thank you. So maybe I can ask, is there another question here in the audience? I can't see any other question. So I wanted to ask a question about so the process that happens for the crystallization. So you see that it starts from the center of the droplet, right?
No, for the binary, it actually, and that's also the point why I don't think that is a binary icosahedral structure, but I think it's a quasicrystal. It started in the simulation from the five-fold symmetry region, but that region was not in the center of the sphere.
Okay.
And the 2 or 3 times that we saw the simulation, because it takes many weeks, it every time was significantly away from the center. So that's exactly why I think that it's not an icosahedral binary structure, but an icosahedral quasi-crystalline structure.
I see. And this would be
the other one. The other one had the symmetry point in the middle of the single particles.
I see. Okay. So not the binary one, the monodispersed one.
No.
I see.
Yeah.
Okay, thank you very much. So I think that we will stop now, except if there's any additional question. Thank you again very much for this talk and the discussion. I think we can thank again Alphonse. Okay, so welcome back for the last talk of this session on gels and energy materials. So the last speaker is Michael de Volder, who's a professor at the University of Cambridge. So here he's the head of the manufacturing group, sorry. So he and his group developed some scalable processes to arrange some nanoparticles, so for example, carbon nanotubes or graphene, into some super structures, which can then be used in many different applications. And today, I think he will be talking about a specific application that is energy storage. So welcome, Michael, and thank you very much for being here. So the talk can last 40 minutes, including 5 to 8 minutes question. So thank you very much, and I think that you can start now. Thank you.
Well, thank you for the very kind introduction. Can you all hear me okay?
Yes.
That's perfect, thank you. So I'm indeed going to talk about a new method using a soft material processing technique, actually, so a phase segregation process. And I'm going to use that to demonstrate how soft matter processes can be used to structure battery electrodes to enhance their performance. Now, I'm aware that many of you may not be familiar with the operation of batteries, and in this case, in particular, lithium-ion batteries. And so I'd like to just spend a few minutes to explain you how these batteries work and make some analogies to help you understand the operation, and I'll go a bit in more details on the soft matter aspects of this research. So first, let's ask ourselves the question, why lithium-ion batteries are worth studying? Well, if you think about it, a lot of the things we use in our daily lives, like laptops and cell phones, are powered by lithium-ion batteries, and they have really shaped the way we work and how we communicate with each other. Some of us might also be using lithium-ion batteries in electrical bicycles when we commute to work, or use batteries to store energy, for instance, from photovoltaics, as proposed by Tesla in the Tesla wall, of which you can see a picture. And then finally, lithium-ion batteries are also very important to power electrical vehicles and contribute to the decarbonization of our transport sector. So let's have a closer look at what the inside of a battery looks like. So in essence, it's quite simple. It consists of an alternating stack of anode and cathode materials that are coated on metal foils. So a copper foil at the top on the anode and an aluminum foil on which the cathode material is coated on the bottom of this slide. And what happens when you charge your batteries is that you're going to pull lithium ions from the cathode, so the particles at the bottom here, and store the lithium ions in the anode. Now, the lithium ions don't like to sit in the anode material at all. And as soon as they get a chance to, they will try to move to the cathode to the bottom. Now, to maintain charge storage, an electron needs to travel with a positive ion. But in between the anode and the cathode, we have placed a separator, which is a porous polymer material, in which there is an electrolyte that allows for the lithium ion to travel through, but the electron cannot go through the separator. So the electron is forced to go through an external circuit to rejoin the ion, and going through the external circuit, the electrons will deliver work to power your laptop or your electrical vehicle or whatever it is that is connected to your battery. So overall, it's quite a simple process. Now, to help you understand this further, I would like to make an analogy with people. So, we sometimes need to go to work, which is depicted by the factory. It's upside down, but at the top here. So we are sometimes forced to go in there. But as soon as we get a chance, we want to go back home to enjoy our lives. And lithium-ion batteries, just like humans, have a two-body problem where sort of one needs to commute maybe with public transportation, and the other one will use maybe car or whatever it is. So obviously, we've been studying lithium-ion batteries as a community for a very long time. And so over the years, people have tried to make the performance of batteries improve. And ways to achieve that include sort of making the housing in which you put your lithium ions more attractive to the lithium ions. So you can make a very nice house which will increase the potential with which the ions want to move back to the cathode. So that would be a high voltage cathode. Or you can cramp a lot of houses together so that within a certain volume you can store more lithium ions, and that would lead to a higher capacity of your device, as depicted here. Now, striking the balance right between having, for instance, a lot of houses packed together, but which don't allow for good transport of lithium ions in and out, or have very fast-paced houses together, which allows for good transport, but doesn't allow to store a lot of lithium ions per square meter. It is a difficult balance to make. And so what I want to do using soft matter processes is to transform the electrodes into something three-dimensional. So more like what we are used to do with houses is to build apartment blocks so that we can store a lot of ions on a small amount of volume, and at the same time making sure that we have a good infrastructure of means to transport the ions and electrons through the buildings. So that's the overall goal. So why is this interesting? Well, if you think back of the cross-section I've shown you of a lithium-ion battery, you'll remember it was sort of this stack of anodes and cathodes, and in the middle we had these separators and metal foils. Now, if we can increase the thickness of our electrodes and make them sort of a three-dimensional thick electrode, what happens is that we need less separator and metal collector foil materials relative to the battery materials, which actually help storing the energy. So just to give you some numbers, in a typical commercial battery electrode, the electrode thickness would be about 50 micrometers, so about the same thickness as human hair. Now, if you would make it sort of 10 times thicker, you would save about a third in the weight and volume of your batteries. And that's, of course, a big deal to battery manufacturers. Now, this is a fairly simple idea, so one could ask the question, why aren't we making much thicker battery electrodes at the moment? Well, you can imagine that if the electrode becomes thicker and thicker, ions and electrons will find it much harder to travel through the electrode. So if you have a thin electrode as depicted on the top here, the electrons go back and forth quite easily. If the electrode coating becomes too thick, the ions will take too much time to diffuse through the electrode, and that will lead to, for instance, very long charging times of your battery. The other problem is that in the current fabrication process of batteries, people take a slurry of the active materials with some binder and conductive additive, and they just cast it on a foil. And if the layer you cast is very thin, it will dry nicely and form a uniform film. But if you try to coat a thick electrode, during drying, cracking and flaking problems occur as depicted in the image in the middle here. And then the final big challenge with coating thick electrodes is that drying the electrode is a very energy-intensive and slow process. So to explain that, I've added a picture here of what a commercial manufacturing line for battery looks like. So this is called roll-to-roll coater. And in the beginning of this line, you have something that's similar to an aluminum foil you would use in the kitchen, which is being unrolled. At the top of the machine here, you squirt some slurry containing the battery materials on top of that foil. And then all the other units you see at the top here are just ovens that are used to dry the battery electrode. Now you can imagine that if you make your electrode coating much thicker, the drying process will be slower and more energy intensive, and therefore the amount of drying units needed would become even more, and so your manufacturing line would become unpractically long. Now, different groups at universities have started studying how we can working towards thicker electrodes. And you can see, for instance, here on the left-hand side, that people have used magnetic particles to create long channels in thick batteries to help lithium ions go in and out. In the middle, people have used salt templating methods to make electrodes. On the right-hand side, people use some advanced carbon nanotube networks. And whilst this work is very interesting, it's not compatible with the sort of large-scale manufacturing processes I described. And also, most of these papers only show a few charge and discharge cycles of the battery, which typically means that after a few cycles, the battery actually dies and is no longer operational. So those are the challenges we try to address here. So first, let's think a bit more about the fabrication processes we have to adhere to for our batteries to be manufacturable at a relevant scale. And so the process used by industry is called roll-to-roll coating. And so you can see an example of such a tool from my lab here on the right-hand side. And although it looks complicated, it's fairly simple. So what we have to do inside is just take a stock roll of metal foil, we tension it, and then we do a process called slot die coating, which is nothing more than just having a little slit in a coating head through which we squirt some slurry containing the active battery materials, which is then dried as I just explained. Optionally, you can laminate it with the protective foil and then rewind your coated battery material. And that's all there is to it, but doing this with thick electrodes turns out to be complex. And so when I started working on these thick electrode sort of concepts, the postdoctoral researcher who was working with me, Dr. Jung-Tae Lee, he had some background in polymer processing and in particular in phase segregation processes. And so what you are seeing here is some work from literature where people studied temperature-induced phase segregation, a process called TIPS in short, of a particular polymer, in this case PVDF, which is a fluorinated polymer. And what these simulations show is how if you dissolve PVDF in certain solvents, it will typically disperse well at high temperatures, but when you cool down the process and arrest it, it can form bicontinuous networks of, on the one hand, the polymer that crashed out of suspension at low temperatures, on the other, the rest of the phase would be the solvent. Now, the reason why we were interested in this in particular is because PVDF is a polymer that's often used as a binder in battery electrodes. So it's often used as sort of cement to keep the particles of your batteries together. So we thought like, oh, well, if PVDF has this property and it's good for batteries at the same time, that might be interesting. The other thing we found interesting is that these phase segregation processes for PVDF can be done with solvents such as PC, which stands for propylene carbonate. And that's interesting for batteries because propylene carbonate is oftentimes used as a solvent in the electrolyte of the battery. So lithium salts are oftentimes dissolved in PC, propylene carbonate. And then these salts in solution form the electrolyte that helps transporting lithium ions from the anode to the cathode. So what we propose in this work then is the following. How about we take the active battery materials that people typically use for batteries. So if you think back of the analogy I made in the beginning of this presentation, this would be the little houses in which we can store ions. So we take those and we mix them with PVDF in the solvent I just described, EC and PC, so propylene carbonate and ethylene carbonate. We mix them all together, heat them up to 150 degrees, and what happens at high temperature is that the PVDF will perfectly dissolve homogeneously in the solvents. Now, if we then cool the suspension back down to room temperature, the PVDF no longer dissolves in these solvents, and it will form this phase segregation process I just described. And so what's interesting now is that we get two phases. One phase here depicted in blue contains the solvent and lithium salts and forms the electrolyte. So it forms a network that allows to transport lithium ions very rapidly through the thickness of the electrode. And the second phase that's formed contains all the little houses, if you want, where you can put the lithium ions in. So we are forming a nice three-dimensional bicontinuous network for storing our battery materials. And so if you look, if you would carry out this experiment and then take the battery material and look at it after drying and removing the electrolyte, you can see, I'm not sure if you can see it well on the screen, but you can see some black holes here, which is actually the holes formed in the bicontinuous network as a result of the TIPS process, and that allows for the lithium ions to move through your electrode. So here you can see some examples of our batteries being formed into little coin cells. So here we have the big black coating. Here is a 2 millimeter thick coating of a battery electrode using a TIPS, so the phase segregation process. And then we mount it into what's called a coin cell. So you can see an X-ray tomography cross-section of a battery here. It's a little button coin cell in which we have located our thick electrodes. And so you can see here on the left-hand side an example of the TIPS process being used for making a thick cathode material. So LFP stands for lithium iron phosphate, is a typical cathode material. And on the right-hand side, we've done the same for anode material using LTO, that's lithium titanate. And so the first thing we did is we checked whether this phase segregation process damages our battery materials, the little houses in which we put the lithium ions at all. And so you can see at the top the X-ray diffraction patterns of our materials before coating the battery material and then after. And if you compare those two graphs, you can see that there's actually no difference before and after the phase segregation process, which means that the little houses for lithium ions are not damaged by the process. Then the next thing we did is we tested the performance of our batteries. And so the first thing we checked is the specific capacity of the lithium-ion batteries. So the specific capacity tells us how many lithium ions we can store per unit mass in a battery material. And so what we've done is in red, we've tested our phase segregated materials here, and we compared them to normal very thin coatings of our materials. So we compare sort of a coating that's maybe 50 microns thick in yellow to ones that's 500 micron thick in red. And we can see that despite the huge increase in thickness of our material, we can still store the same amount of materials, of lithium ions, per unit mass. So it means that the material we are using still performs as expected. The other thing I should show in this graph is that what you are seeing here with the C numbers is an indication of how fast we try to charge and discharge a battery. So 10C is a short for battery researchers to say that you are charging your batteries in just 6 minutes. And so you can see that at 6 minutes, we can store a small amount of energy in our batteries, but if you do it much slower, so for instance, 1C stands for 1 hour charging, 2C for 2 hours charging, and so on, we can store more energy in it. And so I don't want to go too much in these details, but it just shows that our very thick coated electrode performs as expected. And we've done the same experiments for both cathodes on the left-hand side and anodes on the right-hand side. Now, where this becomes interesting is when we start looking at how much energy we can store per area of battery electrode. So if you think back of the little analogy I made in the beginning, if you have sort of a very big sort of houses, you can't store much lithium ions per area, but if you start building apartment blocks, you can store much more lithium ions per area, right? And so that's what we are doing here. We start with a conventional coating in yellow of 60 micrometers, and then this graph shows on the vertical axis how much lithium ions we can store per square centimeter of coating. And you can see that if we use the phase segregation process to make a very thick electrode, we can store much more energy than in a conventional battery. And that's both true for the anodes and cathodes. And you can see, for instance, that by using a phase segregation process for 500 micron thick electrode, we can about double the areal capacity compared to classic electrodes. So the question is, what happens if you make electrodes even thicker? And so here you can see the conventional electrode in green. You can see if we go to 1 millimeter instead of just a half millimeter, we can sort of have a threefold also increase in performance. And then if you go to 2 millimeter thick electrodes, we can double the capacity again. And we weren't able to go to more than 2 millimeters because essentially the casing of the batteries, the little coin cells we are using, they don't allow for electrodes more than 2 millimeters thick to be inserted in there. It just shows how using this phase segregation process, we can really change the properties of these batteries quite substantially. And it's also quite important to check how these batteries behave over long time charging and discharging. So what we are looking at here, at the top, a 2 millimeter thick electrode, which we charged and discharged 200 times in this case, and there was a little glitch in the middle here. But other than that, you can see sort of a fairly slow but constant decay in capacity. And at the bottom, we've done the same, but using 1 millimeter thick electrodes. Now, over 500 charges and discharges, we've retained about 87% of our capacity. So there's actually a very reasonable amount of capacity fade, despite using these very thick electrodes, which is unusual. Normally, thick electrodes tend to lose their capacity very rapidly. And so that's a nice aspect of these TIPS processes. Then we started trying to control our phase segregation process a little bit more. The challenge we had initially is that as we would carry out our phase segregation process, the voids that were created between the active material and the electrolyte phase were quite big. So the amount of electrolyte was very large compared to the amount of active material. Now, in a real battery, you want to cram as much active material together in a small volume as possible, typically, because otherwise your batteries just become too bulky. And so what we've been working on next is sort of taking our phase segregated sort of squashy material and compress it further to try and remove these big gaps in between our electrodes. It's maybe not very clear, but we start off with a material with fairly big black holes here. So those are the voids in which the electrolyte was located. And then by further compressing it, we were able to reduce those by 30%. So here we have a 40% larger void volume than a normal battery. And then here it's reduced by at 30%, as I just mentioned. And so that further increases the capacity. So we've sort of squirted out some empty volume. So what we've done next is sort of we've done some experiments to show that the properties we've measured are not limited to just the two materials I've talked about so far. So far I've talked about lithium iron phosphate and lithium titanate being possible materials for using with this process. And here we show that other popular battery materials such as NMC cathodes, so it's a mixture of nickel, manganese, and cobalt with lithium, operates well with this process also. And so we can combine different types of material to form what people are calling full battery cells typically. Great, so what I mentioned in the beginning of this talk is that it's really imperative to find manufacturing processes that are compatible with how people in industry are making their battery electrodes. And so to do that, we've demonstrated a process on the roll-to-roll process I just discussed. And so how that works is as follows. So we take our mixture of active materials and PVDF and solvents, which I just discussed. We heat that up to 150 degrees, and then we cast that onto our continuous coating process. And initially everything is mixed uniformly, but then as it cools down in the process, the phase segregation will take place, and we form this nice bicontinuous network that allows for thick electrodes to operate nicely. And here you can see an example of several meters of coating on an aluminum foil in this case for these batteries. So the coating was about 10 centimeters wide and several meters long. And so what we also tested then is whether these foils can be twisted and turned, because oftentimes when you take a battery electrode, we'll have to wind it up in a cylindrical cell, and it's important to check that the coating would not delaminate, and that didn't happen, as you can see here. So that brings me to some conclusions I want to draw based on this process. So first of all, I think this is a fairly nice example of how a polymer phase segregation process, or soft matter process essentially, can be used to shape the internal structure of a lithium-ion battery electrode, and in particular by creating a bicontinuous material structure. These processes allow for making very thick electrodes with still good battery performance, which is quite unique. We also have been able to show that it's compatible with a continuous roll-to-roll coating process. And interestingly, because we are using a phase segregation process, we don't need to dry our electrodes, which, as I mentioned at the beginning of the talk, is a time-consuming and energy-intensive process. In our case, we only need to cool down our electrodes from 150 degrees to room temperature, which is less energy-intensive. So we've been able to create batteries with very high aerial capacity, so we can store a lot of ions on a small footprint. And we've achieved very good stability, so 85%, 87% capacity retention over 500 cycles of charging and discharging the cell. The other thing which is really interesting is that with this process, we're actually not limited to the classic sort of coating of a thin film on an electrode at all. So what we, for instance, have done is we've taken a little vial and we just poured our material in two separate compartments in this vial. And the phase segregation process takes place as you just dry your electrodes. You can then stick two metal foils in there and get a battery to work. So you can sort of think out of the box, essentially, as to how you would make your batteries. So there are some limitations to this process as well, which is that you can't use all electrolytes. They need to be compatible with the TIPS segregation process. And so in our case, we used an electrolyte called lithium TFSI. So it's a salt we are using, which is a bit different from what most people use in batteries. I think it's slightly more expensive, so it's a small disadvantage. And the process we developed is also not compatible with certain materials like graphite, which is oftentimes used in batteries. And so that would require more work. Also, as I mentioned, working on the porosity and keeping the porosity as small as possible is important for the overall volumetric performance of our battery. And then finally, a disadvantage I wanted to highlight is that for the TIPS process to take place, you need to add quite a lot of this PVDF, because the PVDF, the binder, is what drives the phase segregation. If you don't have enough of it, it will not be able to control the bicontinuous electrode formation process. So with that, I would like to thank the people who have been working on this project. So Jung-Tae Lee was the main postdoc researcher driving this research, together with Chang-Xin Zhou, who is in the back here. In the meantime, they both took up professor positions in Cambridge and are no longer with us, but they did some terrific job on this project. And I would like to acknowledge funding from EPSRC, ERC, and Marie Curie on this particular project. So thank you for your attention. I'll be very happy to take questions.
So thank you very much for this talk and exciting news for new applications. So are there any questions for Michael? I can see, yes, so there's a question here.
Dan Frankel, Cambridge. Thank you very much for this very nice talk. You mentioned the fact that you wanted to decrease the size of the holes in this matrix, and as I understood it, it was by compressing the material or something. But they're formed by spinodal decomposition, and so you would think that if you change the quench conditions, the holes would already naturally be smaller, or you could make them smaller. Is that at all an option, or are there reasons why you didn't explore that possible route?
Yeah, it's a very good question. So the thing we struggled with is that, especially the holes are in effect the place where the solvent driving your process is located. So if you want to make the holes smaller without having to compress, we need to put much less solvent in the material at the beginning of the process, if that makes sense. Now, we found that if we reduce the solvent amount too much, then our material became almost sort of solid to start with, and the phase segregation process won't take place anymore. So that's where we ran into problems. But yeah, otherwise your approach, as you suggested, would make much more sense than trying to squeeze things out at the end like we did. Yeah.
Thank you. So there's another question.
Hi, so Daniel Reed here. I was trying to work out whether the spinodal structure is entirely optimal for what you want, because one thing about the spinodal structure is everything is the same length scale, and what you're trying to do is get the ions in and get them out again as efficiently as possible. So I was thinking about structures like lungs or other things where you have large holes and smaller holes and smaller holes and smaller holes and smaller holes still, and whether actually some structure like that would be more optimal if you could control the phase separation to do that.
Yeah.
And I'm not sure whether you can do that by a sort of gradual quenching, because if you quench a little way below the phase boundary, you get large structures. And if you quench a bit further, you get smaller structures. And I wondered whether you could sort of do a sequential quenching to sort of get something like that.
Yeah, I mean, that's an excellent suggestion, which I had not thought of. So what I did think of is that this structure is not ideal for a number of reasons. So the first one is the tortuosity, so the length the ions need to travel through the electrode to go from one side to the other. In an ideal case, it would be just a straight line and not a tortuous path. So that's one thing that's not optimal. So if we could get the phase segregation to create holes that go straight down, that would be better. And then certainly, like you said, sort of, parts that sort of would gradually become smaller would be better. Sort of, again, I'm using this analogy with cities too much, I think, but sort of it's like having a highway and then small streets that sort of come off it, and that makes a lot of sense. So if you think that there's a way to sort of achieve this by controlling the quenching states, that would be really interesting actually, and sort of we could think of having bigger channels at the top and then smaller towards the bottom, and so that would be very nice follow-up work to consider. And I'd love to chat of it longer, maybe offline at some point, but yeah, it's a very interesting idea.
Yes. Thank you very much. So we have a question online by Emanuela Delgado. So she says that during cement hydration, one ends up with a solid with very fine, I will start again. There was a typo. So during cement hydration, one ends up with a solid with a very fine network for connected small pores. Would that be interesting to think about this type of material?
Right. Well, I mean, by the sounds of it, it's very interesting. So I'm not familiar with this particular process. I'm more familiar with sort of battery processing classic ways rather than the process suggested here. But certainly, if you think that would lead to interesting pore structures in our batteries, then I'd be very interested to look into that and collaborate. So please feel free to to get in touch. But I can't comment on it really because I don't know the process myself, which you're talking about here, but it sounds
Interesting, yes.
interesting.
Okay, yes, so if Emanuela, who's expert in this ways to develop new cements, can get in touch with you, that would be great.
Absolutely.
Okay, great. Are there any additional questions, either online or in the audience? We have another question here in the audience.
Hello, Malcolm Pears from Bayer. Just following up the question from Daniel, have you thought of looking at, say, having 2 phase separation processes, as you call it, down, so you could have a hierarchy of different structures?
No, I've not thought of that, but it's again like an interesting idea. One thing you have to keep in mind is that sort of batteries are fairly hostile environments for lots of materials, and sort of the materials you can play with are limited. And so PVDF, for instance, it happens to be very stable and good for sort of cementing battery materials together, but maybe just playing with sort of the molecular length of the PVDF and have sort of 2 types of PVDF in there, maybe that might lead to something interesting, for instance. Or I would have to look more carefully at sort of which other materials would lead to good phase segregation process whilst still be compatible with what someone would like to put in a battery. But they are very interesting ideas, and certainly sort of the easiest way to do it I can think of is just working with maybe 2 molecular weights of PVDF and sort of see whether that leads to some interesting new phenomena. Yes, thank you for that suggestion. If you have other ideas, please let me know.
Okay, great. So there is one quick question, one last. Yeah, no, I mean, we have time for an additional. There's another question from here in the audience.
Hello, my name is Lawrence Harris from Mondelez International. So it sounds like solvent minimization is an interesting sort of avenue for you for reducing pore size and volume. You mentioned that when you drop down the solvent quantity, you start to have a solid mass that I guess you can't deposit onto the foil anymore. What's driving that? Is it that you have a suspension system which is now just getting to a jammed state? And if so, I see cement's been mentioned. Myself, I work in chocolate. Jammed suspensions and trying to get maximum flow and minimum continuous phase volume is quite a lot of industries have that challenge. Is that the mechanism that you're struggling with here? I wonder if there are some commonalities around how other industries solve their dense suspension flow problems.
Yeah, I think it's very much a jamming sort of problem. It certainly feels like it when you're trying to process the material. And so we are, I think your suggestion to draw from other fields where people are facing similar problems to minimize the amount of solvent is something we should definitely look into. I mean, we've used the brute forcing method so far to just squeeze out the solvents at the end, but it's not as elegant as what you are proposing, which is to really optimize the sort of minimum viable amount of solvent while still having something that flows. Yeah.
Okay.
And if there's lessons to be learned from how people process materials like chocolate and so on, and that certainly would be useful for us.
Okay, great. Thank you very much again. Thank you for this talk, and thanks to all the speakers of this session.